Ladies and gentlemen, please welcome the Director of DARPA's Microsystems Technology Office, Dr. Bill Chappell.
All right, today I'm going to talk about the intertwined history of DARPA and Moore's Law. And what I'm going to convince you of is that Moore's words that he wrote down over 50 years ago today are more important now than they were when he initially stated them. Now, that's a big statement, because if you look at what he actually did, right, he charted the course for the electronics field for the last 5 decades. Right? What he said was, staring at 50 transistors, that packaging was so expensive that the more I'm going to be able to cram transistors onto an integrated circuit, the more I'm going to be able to afford, right, for my next generation. And that we're going to keep cramming until I hit the end of my yield. And that's going to advance year on year. And he set the pace at which electronics is going to advance. And he was only looking at 50 transistors and projecting out to 65,000 transistors in 1975. And it was a miracle. He captured a miracle, a one-way engineering trade-off, where if you make things smaller, right, you make things better. You get more of them, you get more functionality. They're going to operate at lower power. Right? That's not supposed to happen. Right? And capturing that over the last 50 years and having it invented initially at Bell Labs as a transistor at Bell Labs, and then Moore's Law being paced as a US-centric capability has been important for this country. If you look at the implications for our economy, you would see over a 2-decade period in which Moore's Law was thriving, what you'd see is that GDP growth was around 85% for our country, right, and over 265%, right, in the semiconductor manufacturing industry. Right, we have electronics as the 3rd largest export, right, second only to automobiles and aircraft, and this is one where our peer adversaries import more electronics than they do oil. Both China and Russia are in the uncomfortable position of relying on our capabilities, often for their systems. And it's a race that's as intense in semiconductors as in any other field. We plow more money back into R&D from revenue than in any other field, including high-tech fields like pharmaceuticals. But of course, this is an area where economics, right, and national security are completely intertwined. Right, what's good for the economic health of our semiconductor industry is actually good for our national security. If you open up the hood of any of our military systems, how we see you before you see us, how we process that information, how we disseminate that across the battlefield, right, is dependent on the quality of the electronics inside of our systems. So capturing an exponential for over a 50-year period is obviously a very important core capability and foundational to the society that we have today. So what Moore stated was incredibly important, but what he stated next on the next page, I think, is actually more important. What he says in Section 8, the Day of Reckoning, is that we're going to keep cramming our circuits into a monolithic chip, right, up until a particular system function is no longer minimized. And that's important because that's an economic argument. He's making an economic argument that we are going to do this, right, as long as it makes economic sense, and that was true well beyond he ever envisioned. Well, here we are today. If you actually look at the double edge of Moore's Law, is that we've had performance like flops exponentially increasing over the last 50 years. Right? Our operations per second have linearly or exponentially increased, right, over 5 decades, but we have a new exponential, and that exponential is the cost of a development of a system. From the fab, right, which could be in billions of dollars, to the design, to the verification, to writing the software for a modern system, right, we have a exponential growth across the board. We just had our ERI summit. NVIDIA came and displayed the latest and greatest product, the heart of many machine learning systems, and they said, we developed this at the bargain basement effort of 8,000 engineering years. That's $2.5 billion. Right? So when you're living in a world where it's $2 billion or $3 billion to develop a system, obviously you can't experiment. You can't get that wrong. So Moore correctly predicted where we would be today, but what he didn't predict, right, is the full complexity bind that we're facing. Lynn Conway describes, right, the bind of complexity that we're facing into the 70s, and we're here again, right? And it's not just cost. He got the cost vector right, but he wouldn't have predicted. Right? Their foreign adversaries are investing $150 to $160 billion, right, to poach or at least replicate our electronics industry. Non-market driven investment, completely distorting the market that exists, that we rely on. It's also rising stakes. At the same time, right, as we're trying to figure out how to run the race faster, right, in a distorted market, you now have this emergence, right, of the cyber threat, right, which is expressing itself all the way down to the semiconductor layer. You're trying to make design choices to increase performance, but you don't know if in 10 years someone's going to figure out if the design trick that you just used is now going to be used against you. And we have addicted the world to this digital capability that we're all very proud of, except when you create a crack in the foundation of that digital society, right, everybody is going to pay. And that's the complexity bind that we face today. And that is the backdrop in which we created the Electronics Resurgence Initiative. $1.5 billion over the next 5 years in the foundation of electronics such that it works for the US and it works for the US national defense. So we went back to the drawing board and said, what else did Moore predict? Right? He got the last 50 years right. He got the present that we're facing right. What did he say about the future? He said, maybe, right, we can look at materials integration. Maybe it will prove more economical to build large systems out of smaller functions. What if we just blew up the last 53 years? What if we exploded it into smaller pieces? Right? What would that world look like where I can now mix and match small building blocks to create the systems that I'm relying on? He also said, perhaps, right, we can create newly devised design automation procedures that can translate from logic diagram to technical realization without any special engineering. He's calling for a revolution in EDA, the ability to have high-level descriptions of function and go all the way to the physical layer, taking out, right, that 8,000 engineering years required to get a system into the field. And last but not least, he's describing building blocks that can be repurposed from system to system, exploring different architectures. In total, what he's talking about is rapid design, quick assembly of new systems, and exploration of new types of architectures, going from the last 50 years where we relied on general capabilities and abstraction, right, to a new line of advancement, which is all about specialization and uniqueness. So what does that look like? We announced 9 programs under the ERI banner last September, one of which I'll describe here, which is CHIPS, very much in line, exactly what Moore was talking about. It may prove more economical to build large systems out of smaller functions. We take 50 years of cramming, right, and we blow it up. Now we look at heterogeneous integration of smaller building blocks. This might seem trivial, right? But the implications across the industry are huge, and for the DoD, it's foundational. 8,000 engineering years, right, is the amount of time it takes to create an SoC. We're not going to do that within the DoD. But I can build an accelerator. I can build a security block. I can build a chiplet that goes into a system, right, which allows me to upgrade that system to handle the needs that the DoD needs that are specific to us. We have performance, right, that is outside of the commercial mainstream. We have security concerns that are outside the commercial mainstream. This gives us a vehicle, right, to create unique systems, but partnering with our home team. NVIDIA, Intel, Qualcomm, AMD, these are the chip manufacturers that define the electronics industry. We're very lucky to have them on shore. Partnering with them, with our defense base, we can now create hybrid systems, right, that are better than anyone's ever invented in the world by looking at this heterogeneous integration. But it's not just allowing for these partnerships to thrive. Now, if I have a new material, I can add this into this heterogeneous mixture. I don't have to beat silicon. You're not going to beat silicon. It's got a 53-year head start. Right? That's a 53-year exponential that you aren't going to be able to invent in your first couple of years of an invention of a new material. But I can now add new exotic capabilities. It can be different than silicon. And I can be different in silicon for something like an accelerator. Right? And it can just be weird or different, and it doesn't have to be better in every aspect of processing logic. Right? And I can add that into the mixture. I can go vertical. Right? I can integrate with new manufacturing steps like what we're doing with Stanford and MIT, which is carbon nanotubes on top of 90 nanometer silicon. And we're showing that algorithms, next generation machine learning algorithms, work better in a vertical stack than if you actually have the memory and the processing next to each other. All right, so here's this heterogeneous mixture of capabilities. We can auto-generate either the core of the system or the attachments, the accelerators, the building blocks that are going to go on the side. We demonstrated with Berkeley the ability for a design team of 2 graduate students to write high-level code and go from that high-level code all the way, right, to the physical layer. Right? These are the building blocks at which ERI is built upon, right, which we're going to go from that generalized and abstracted view of the world to a specialized and unique view of the world. So when Gordon Moore heard about ERI, he wrote a letter, and he very humbly said, right, since the paper I wrote that ERI references, I would never have believed in the last 52 years is far beyond anything that he had contemplated. Right, very humble. Right? But what he also says is there's a testimony to the creativity of the many engineers and scientists that the industry has surmounted apparent roadblocks that look to be the end of the transistor scaling. What he's saying is he made an observation. It's the community who turned it into a law. And DARPA's been there every step of the way. And we're going to explore that throughout this session. We're going to talk about the decisions that we made through the course of that history, a 50-year exponential that's been good for the United States by simultaneously being good for the world. And we're going to explore the self-sacrifice that it took from both the program managers and the community, right, to be able to make this work. We're going to look at Bob Kahn, who's known for his TCP/IP work and his networking work. We don't think of him as someone was foundationally important in creating the VLSI program, right, which shaped the way that we now create circuits. We're going to talk to Lynn Conway. Lynn Conway, with her partner Conway Mead, wrote the textbook that gave us the blueprints on how you're going to make, right, circuits disconnected from the fabrication facility. That changed foundationally how the industry interacted. She took the results of the ARPANET and the work that Bob Mead was working on and showed the impact of it by decentralizing the design, allowing for design to happen in one place and then manufacturing happen in another place with the internet as both the collaboration medium, or the ARPANET, the ARPANET as the collaboration medium and the file transfer mechanism. Then she joined DARPA and continued that revolution. Along the way, we did things like invent 193 nanometer lithography. We invented the FinFET with Berkeley. Right? We passed that off to industry. They perfected those capabilities and they became part of the industry. But I also take people like Mark Papermaster, who's going to join us, right? First working at IBM, then at Apple, and now at AMD, right? Harnessing the complexity, turning that underlying complexity into products that we all can use. And it takes people like Andreas Olofsson, one of the newest members, who raised their hand and said, it's my turn for national service, quitting his job, making some of the most interesting chips that we have today with very small design teams, raising his hand and saying, it's my turn for national service. I'm going to lead the community, reducing the barriers to entry so anyone like me can make progress in a domain that's only good for large entities today. So we're going to explore this pathway, starting with Bob Kahn.
So, thank you, Bill, for those nice opening remarks. Welcome, everyone. I'm happy to be here. As Bill mentioned, I'm probably more known to many of you for the work I did on networking, ARPANET, and the internet with my colleague Vin Cerf. But while I was director of what was then called the Information Processing Techniques Office, we had a major challenge facing us, and it is what really caused us to get very deeply into the VLSI range, not so much as a technologist, but as an impetus for moving the field forward. So I want to give you a little sense of what that's about. And I was asked not to use slides, but it's a message that I think you really need to understand. Because it wasn't like everything just moved along smoothly. DARPA really did play a major role in this whole thing. So in the 1970s, because of the Vietnam War and because of the major negativity expressed by many in the research community, a lot of people walked away from DARPA funding, and the Congress reacted accordingly. The Mansfield Act was passed, and the amount of actual money going into computer science research in the 1970s dropped by about 75%. So there was a real kind of existential challenge to that whole field. And when I took over running the IPTO office, the challenge that I had was how to revitalize the computer science community. People were feeling demoralized, funding was going away, people were dropping out of the field and going into other things. So fortunately, there was a confluence of technologies that occurred at roughly that time. For example, there was networking, which made it possible to make distributed systems happen. Computers and communications had been different disciplines, but they came together, and computer communications then became a field in its own. The whole world of VLSI was not really one that was accessible to the research community. They were basically used to dealing either with large discrete components, which they could assemble architecturally. But we knew back then that there was a real potential that if the university community and those in industry who had really interesting architectural ideas but couldn't leverage them could get into the field, that maybe this would be a start. And that, coupled with strategic computing, which came thereafter, really restored the whole computing field to where we had thought it might be before. What was one of the goals was to take advantage of what we thought was the innate innovation in the university research community. It wasn't being leveraged. It'd be like trying to do computer programming where you never had a computer to work with, so you could never test the results of what you had. And fortunately, at the same time, we were fortunate in having enough money to go stimulate the industry to build high-powered workstations and systems that could support the kind of large files that we did. So we supported like the work at Berkeley on virtual memory Unix and things like that that enabled the community to be able to process these large files. Now, ARPANET was a major process in this. We were trying to create this community. Meanwhile, as you'll hear from Lynn Conway later on, she was trying to demonstrate how you could get multiple people to kind of get their ideas in a particular way using multi-project chips. And she approached me one time and she said, would it be permissible from DARPA's perspective if we allowed some of those designs to go over the ARPANET to our staff out at Xerox PARC? And we agreed to do that, and so we collaborated on making that happen. But in starting this program, which I did at DARPA, I was motivated by a paper that was written by Ivan Sutherland, Carver Mead, and Tom Everhart, which laid out the future for submicron technology. And I knew, instinctively, that if you're going to build chips that had millions or hypothetically billions of devices on them, it wasn't enough to do that in memory alone. We're going to need computer assistance to do that. And so that was what the VLSI architecture and design program was all about, that I started back in the late 1970s. But in order to make this reasonable, we needed a research community, which we decided to fund, but that was only going to be useful if they could get their ideas fabricated really quickly. We needed a fast turnaround facility. I tried several different ideas, but eventually we decided to piggyback on what they had done at PARC. With PARC's help, assistance, and in fact encouragement, we transitioned that to the University of Southern California, and we set up a system there called MOSIS, M-O-S-I-S. The fellow who ran it, Danny Cohn, wanted to call it M-O-S-E-S. We ended up calling it M-O-S-I-S because it was an MOS implementation system. And you know, I think it really started in large scale, all of the work on fabless design. Now, we were very fortunate that at the same time, there was a textbook that the community could use that Lynn was involved in writing, and so there was a methodology laid out that they could all deal with that. But DARPA made the decision to piggyback on top of that, to adopt this multi-project chip design thing. We funded some work that led to standard artwork format called SIF that was widely used. And of course, the book made it easy for us to train teachers and build a whole community, again, with a lot of people participating. There was a lot of sharing of designs, multiple meetings that we went to, and the like. Back in those days, this was not necessarily easy sailing, because at the time we were doing this, the Pentagon was trying to set up a program called VISIC, very high-speed integrated circuits, and that was a very classified, defense-oriented program. And so we had these twin tenets of do we work on the near-term defense-related things, or do we work on the long-term research things which potentially could benefit defense as well. This was never a battle that was really sorted out, but it made for tense times back then. The role of strategic computing was really important in building out the internet infrastructure. And over the years, we funded a very large number of research projects that led to very interesting kinds of capabilities. But I would assert that without this concerted and focused and targeted defense push out of DARPA to help make VLSI real for the community at large, a lot of what you now see happening would have either not happened at all or be quite severely delayed. So I thought that perspective would be interesting for you, and I think I'll leave it there. Thank you.
Thank you, Bob. Got a lot of questions we'll ask in just a second.
All right.
So.
All right.
All right, so there's a lot of ways to change the world. Sometimes it's a DARPA office director stepping in and amplifying an opportunity. Sometimes it's writing a textbook and showing the world through education, right, that a new design paradigm is afoot. And so, Lynn Conway, would you join me?
Many thanks, Bill. It's a thrill, such a thrill to be here at DARPA's 60th as we reflect on where we've been and ponder where we're headed in electronics. As some background for our panel, I want to give a little overview of DARPA's pivotal role in the VLSI revolution and how the new VLSI technology and the ARPANET began synergistically co-evolving in the late 70s. And what's interesting is we've enjoyed 4 decades of breathtaking progress ever since, and what a trip it's been, looking back on it. But with the plateauing of Moore's Law, many folks now see the road ahead blocked by looming complexity. And in great contrast, as we're hearing today, we envision exciting breakouts into vast unexplored territories. So how do we see that? How do we reason that? Well, there's one way to think about it as follows. As an old-timer at 80 years old, I've lived through something like this before, almost exactly like this. Namely, the complexity bind that faced microelectronics in the mid-70s. Lessons learned back then seem directly applicable now. So let's go down a little trip on memory lane, starting in '75, just before the VLSI revolution. Back then, microprocessors contain about 7,000 transistors. And inside the fab houses where they were designed and manufactured, specialists in computer architecture, logic design, circuit layout, and process design all worked together inside separate silos of their own on the overall design of a chip. And what's interesting, as you went chip to chip, each of those specialties independently optimized its work. And overall, complexity grew by leaps and bounds. So let me just give you one example. Circuit layout, just at that one level, involved, at that time, about 40 pages of complex design rules. They were used for hand crafting, hand carving, and hand checking giant Ruby lists that were put up on walls and overlaid to check for design rules. And those were then photographically reduced to make reticles and masks. Now, right around then, Dennard scaling suddenly exposed an incredible possibility, namely that under Moore's law, working chips might contain as many as 1 million transistors in about 15 years, by 1990. But you see, no means existed for designing such complex chips. It was as if printing had been invented before written language. Now, in a burst of, kind of a wild burst of collaborative research at Xerox Palo Alto Research Center and Caltech, we evolved a set of new structured VLSI design methods that displaced these over-specialized traditional specialties. For example, at that extraction level of simply the layout design rules, get this clicker working. There we go. At that level, we invented a concise set of scalable, dimensionless layout design rules that were usable in very simple graphical EDA tools running on personal workstations. Not only that, but they provided a precision digital interface between design and fabrication. So design could be done separate from fabrication design. The overall Conway methods enable even novices to do top-to-bottom architecture and design of silicon systems. We drafted a textbook on the methods using the Alto personal computers and laser printers at Park. These were our secret weapons in asymmetrical war on the outside system because people didn't really realize tools like that existed back then. And then we used that text to teach an experimental VLSI design course at MIT in the fall of '78. Students quickly grasped the new methods and did chip projects that were fabricated at HP labs afterwards. The results of such fabulous design included, guess what? A Lisp microprocessor designed by Guy Steele, just one of those students' projects, a Lisp microprocessor, his very first design. This stunned the industry, and many other schools wanted to offer MIT VLSI courses. And of course, I then struggled with, well, how on earth could you scale this experience? This is like a one-off, hit the beaches, landed, and survived. Now, how do you break out? Well, this led to the conception of an e-commerce system that enables students at various remote sites to send design files via the ARPANET to a remote server at Xerox PARC. Not only that, but to interact with the server via email messages highly encoded to keep track of the overall progress of the course, the rules of the game as they went along, how many chips from that school were likely going to make it into the wafer set. That server software at the design cutoff would pack them into files for multi-project wafers to be made in a silicon foundry, again, for example, at HP. And here's what the software looked like. Just an overview. Then, taking a huge risk, this is sort of along the lines of, it's better to beg forgiveness than to ask permission. My little team at PARC announced to the major research universities in the United States that were on the ARPANET, if you run Lynn Conway courses this fall, PARC and HP will fab your student projects. Let's think about that. 12 schools took the bait. And what became known as MPC 79 exploded into a pretty wild ARPANET happening that fall. And in early December, 129 students and researchers sent in scores of innovative designs, and the chips were returned from HP's, quote, foundry in January. And here's the sketch of the overall process. I'm going to come back to this. And one of the chips in this set, there were 129, there were a tremendous number of exciting ones, but let me tell you about one of them. One was the prototype geometry engine designed by Professor Jim Clark at Stanford that led to his founding of Silicon Graphics. Okay? Now, again, you can kind of look at this and you see from top to bottom, it's all code. It's code, 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 going to the internet, specifying layout patterns, pattern mask making, wafer fabrication, splitting them up into chips, taking each little chip out of a multi-project set of chips and packaging it for the individual designer and sending it out, kind of like doing an Amazon on it. Well, MPC 79 demoed and validated the design methods, the book, the courses, the EDI tools, and the e-commerce system. Running at scale now and in sync. You know, all these courses running in sync. Think all the universities, all the faculty members, all the students. What it did is it bootstrapped a VLSI technosocial ecosystem. And all along, I'd been interacting with DARPA because one thing I did ask permission for was, you know, we're going to do this on the ARPANET, you know, and I'm not sure this is going to work, but so it was okay. So Bob and I had been interacting during this lead-up phase. And in 1980, DARPA founded their VLSI program to support explorations in this new frontier. And also in 81, the MPC 79 technology was transferred to USC ISI and became the MOSES system, which was supported by DARPA in the following years, thus helping exponentiate a whole community of VLSI researchers having direct access to experimenting in real silicon. Now let's take a closer look at Figure 11 and envision the symbiotic coevolution of VLSI and the ARPANET. You see, if you take one run through this as sort of one cycle at one node of silicon design, each major iteration of this technosocial system, the VLSI chips embedded in computer workstations and ARPANET routers and servers enable the design of VLSI chips for more powerful workstations, routers, and servers, which you then embed into the next iteration of the game. So the games rerun using the next node's VLSI chips. And a way you can kind of think about this, if you step back, go meta on it, take the 10,000 meter view, the dramatic results mirrored the synergistic exponentiation of railroads and telegraphy in the 19th century. Do you see how those things go? You go look at the charts independently of the revolution, and they lay right over each other. Well, some reflections on all this, maybe some lessons learned. Reflecting back to those design rules, man, that's just one level. There are all the levels were simultaneously restructured. The accumulation of local complexity is akin to hoarding. it continually wastes both human and machine time and energy. Needless complexity should be continuously deconstructed. And its deconstruction should be highly rewarded. Upon simplification, specialties are more easily cross-visualized. Teams can see each other's forest for the trees, and cross-cutting disruptive innovations are more rapidly made and disseminated.
I don't have a grade book.
In all of this, including when you look at that diagram and think what was going on at all those schools, open team competition is a vital form of collaboration. The students in each course are competing, the student teams. The schools are competing. All this is open. There's, even to this day on the internet, there are photographs and descriptions of all these projects and who did them. And so that kind of competition makes all the activity visible and helps select innovations that improve the overall game, such as Jim Clark's chips, silicon graphics, which made more powerful workstations, and on and on. Such technosocial dynamical processes involve humans and their tools within all feedback loops. So really importantly is innovation in user experience design and user experience inclusion are central to the empowerment of these systems. And I guess last but not least, always remember narrow expertise has a half-life. And that half-life gets shorter and shorter in times of accelerating technosocial change. As the philosopher Eric Hoffer said, in a world of change, the learners shall inherit the earth, while the learned shall find themselves perfectly suited for a world that no longer exists. Thank you.
Thank you very much. All right, our next speaker's job is now going to talk about the present, right? The theme of this is past, present, and future. Mark Papermaster's job is to harness Moore's Law and turn it into products that matter. I will just say that when he was at Apple went up around, let's see, I got a number, 143%, right? That was the stock increase. You think that's pretty impressive? And to compare it to AMD, right, which is now up 480% since he joined and took over as the silicon developer. So apparently, capturing an exponential is a good idea, right, and can be profitable. So everyone, welcome Mark Papermaster, and we'll find out where he's going next so we can all invest.
Great. Well, it's really a pleasure to join you all this afternoon. And Bill, thank you and DARPA 60 for the opportunity to speak along with really esteemed panel here. And I love the title. When you look at Electronics Resurgence, that is what we are in right now. It's pretty amazing when you look at the kind of change that we're looking at right now. And you know, I say that, and you can say, well, wait, it's been nothing but change. Look at Lynn's last comment about the half-life of any technology that we're dealing with. What we do in electronics has been nothing but change, no doubt. But how we've been practicing the trade since the birth, since we went to scale of design rules, since the ARPANET leading to the internet, we've enjoyed Moore's Law. And I love Bill's opening comments about the truisms that Moore's Law brought us to where we could drive innovation on top of a truism that we would really double the kind of performance while staying in that cost and power envelope every 18 to 24 months. And it's been fantastic, and it's driven and fueled phenomenal change over the last decades. But why is it this resurgence now? Why is now yet another era that we're facing? And I think it's pretty clear. I think you all see it every day because you're driving it. You're driving it because you're demanding a change in the way that you deal with computing. First, simply the way you interface with it. It starts with a retina, the high resolution displays you got in your, in an iPhone and other mobile devices back 8 years ago, and you look at how that's driven your expectation of your visual experience. You want a great experience. You expect a great visual experience. And it's even more than that now. What you want is to be immersed. You want that information. It might be your home life or it's your entertainment, or you want that screen to be big. You want it to be high definition. You want the sound to be integrated with that visual experience. And then where do you see it going? Well, around the corner, it's going to be immersive, because you're seeing virtual reality and augmented reality coming around that corner. So we are demanding a better visualization, a better interface with computing, and we're getting it. But it's driving more and more computational power. Likewise, every day at your home, at your work, at your applications, you're depending on massive data, instantaneous data. All of the embedded devices around you are providing that real-time information to you, and it has to be processed. You want it back real-time. You want it to be real-time analytics. You want it presented to you back in that visual experience. You want it presented to you in a way that you can put it to use. And so your expectations of computation are going up. And in fact, you actually want it to anticipate. You want it to leverage the whole history of data that came before your current point in time. You want to leverage that data and harness it, and that's what machine learning has done. It's allowed you to analyze that data and be more predictive on a given set of applications. So all of this together is driving a massive demand of additional computation in every walk of our day-to-day life, at home and at our work applications, our industrial applications. So going back to Moore's Law, it's not going away, but it's different going forward. We're still getting the density improvement generation after generation. We're still able to pack more and more transistors. But that inherent frequency boost that sort of brought the performance of every application up at every node, that's going away. So it's not the same. And in fact, when you look at it, the costs are going up. So you just look at that factor from going from the node that most leading edge products today are at a 14 or 16 nanometer node, and they're moving next generation to a 7 nanometer node. And you look at that cost per die, and it's roughly doubling. So frequency leveling off, cost going up. Yet, what's the trend say that we've done over all of these years? We have been doubling, not quite every 2 years when you look at this amalgamation of data, but we've been doubling system level performance and performance per watt of energy, because you're energy bound in most every application that you run. We've been doubling about every 2.4 years. So what does that mean? It means that we've been already having to manage complexity in our design process. We've already been having to harness the slowing of Moore's Law along the way. How have we been doing that? Well, we've been, all of us in the industry, improving our design techniques, thinking about it at system level, right? Looking at the application and how we can integrate more. Typically, till now, it's been still monolithic on a single die, but we've been able to ride this curve by adding system innovation, creating, you always hear the term system on a chip, bringing more and more of those system functions in closer together and staying on that performance curve while fitting in those power boundaries that don't change. You look at a socket of server. It's anywhere from 150 to 200 watts for a single socket in a server. You look at a PC application. It's anywhere from 15 to 45 watts if it's going to be in, let's say, a notebook class of application. And then the mobile devices, they have to be simply a handful of watts. That doesn't change. So you've got a bound situation. You have increasing complexity, and yet we have to stay on this curve. Our customers demand that we stay on the curve. And so how is that going to happen? It's an evolution of Moore's Law. The technology process node still matters. It's still vitally important. You saw those density improvements. And those density improvements that you're seeing on new process nodes I think they're going to, I'm hoping that they actually track with those cost improvements. So if you can, let's say if you could double the number of transistors while that cost is doubling per node, then you can at least maintain an equilibrium. But that's not going to keep us on that 2.4x pace every 2 years. And that frequency rolled off, that's flat, so we need new levers. And that's what I call Moore's Law Plus. It is thinking differently about how you integrate the functions that you need to keep on that curve. It's thinking about architecting for multi-chip solutions. It is going back to that prediction of Gordon Moore, where he said it will take these type of heterogeneous solutions that you can piece together. He's absolutely right, but we have to be able to do it in such a way that you architect from the beginning. Just like you heard in the earlier session about, you can't lay the concrete and then come back and figure out how to put the conduit in. You have to, of a new house that's being built. Well, it's like building a house as you're thinking about the next generation of processing. You have to architect it up front of how you're going to have a multi-chip. You need to think about your packaging, all of your interconnect, and what different type of processing architectures you get together. And you have to work across the industry, because the way this works is you have to create an ecosystem. That is an ecosystem that we heard about, that Bob and Lynn brought to us, that DARPA was the risk taker and supported that and brought that ecosystem that started the VLSI revolution. It's going to be the same type of ecosystem that needs to be developed and nurtured to keep us on this pace. So you have an ecosystem where multiple chip architectures can play together, can interconnect and talk together. And the last point is the biggest point. It's not just about hardware. It is an electronics resurgence, but electronics going forward is equal parts hardware and software. And so the software investment has to equal all of that we put into the hardware. And it needs to be in such a way that you can put solutions together that can be deployed with hiding complexity. And that's what you're seeing going on with machine learning applications today. It's enabling end users to write at a very high level language and use the frameworks like TensorFlow, Caffe, and others. These hide the complexity underneath, like scalable design rules did years ago for VLSI. These frameworks hide the complexity and are enabling us to take advantage of this massive data and create machine learning applications and high-performance compute applications. So when you put all of that together and you look at the kind of new approaches that we're bringing to electronics design and chip design going forward, I have complete confidence that we're going to stay on that pace of system design at a given power envelope, improving it not only 2.4x every couple of years, but I think we'll exceed it. There's phenomenal innovation going on in the industry right now. And I look at the DARPA initiatives, and I think it's going to spur us on at even a faster pace. So thank you very much.
Thank you. All right, one of the best parts of my job is scouring the country for talent, and not just talent who will quit their jobs and join the government for national service. And sometimes I find that talent, and sometimes that talent finds us. I got an email from Andreas that said, that $100 million program that you're running, I've already done it. And it's like, I better talk to that person. Not only do I want to talk to that person, that's the type of attitude I want to bring on board. So we're very lucky to have Andreas Olofsson, who led a 4-person design team, right, trying to clobber some of the AMDs and Intels of the world, and did as good a job as you possibly could with a small design team. So we brought that into the government to represent the opportunity of lowering the barriers for new electronics. Welcome, Andreas Olofsson.
Thanks, Bill. Yeah, so I spent 9 years trying to compete with Intel, AMD, and everybody else. I realized it was a losing battle, and so I joined DARPA to try to solve the problem for everybody. So, let's see. So we heard from Lynn and Bob about the complexity bind that they were in the 1970s. I would argue that much of the dominance that we have today and that we've had for 30 years in the global semiconductor market is thanks to that silicon revolution. And then we heard Bill talk about the much overdue complexity bind that we're in right now. So in a way, it's time for a second silicon revolution, and that's what I'm going to talk about today. So if you look at modern devices, like the devices designed by AMD and others, they're amazing achievements. We're talking about 20 billion transistors, tens of miles of wiring on the chip, millions and millions of lines of software running on it. And they get it right. Almost every time, it's a first-time success. But they're very large, right? They can spend $100 million or even billions of dollars per platform to create those things. And thousands of engineers with very specialized knowledge to achieve that. So clearly that's out of scope for small startups. It's also out of scope for DoD. So we should do something about that. We should enable Moore's Law power for everybody that needs it. So to give you an idea of what this complexity looks like, because probably there aren't too many chip designers in here, if you can imagine, right, standing outside the National Harbor, right, and you take out a piece of hair, right, so about 100 micron in thickness, you put that down in front of you, and then you continue ripping out hair, which is kind of like what chip design is, and you lay those down in front of you, go out to the 495, and you continue doing that until you get to Baltimore Harbor, right? That's the length of wiring that we have on a chip today, right? Now, if a single piece of hair gets out of place, you just lost $100 million. Right? That's the mentality and psychology of chip design today. So that is brutal, right? Now, within ERI, we are going to try to reduce that design complexity barrier as close to zero as possible. So in essence, the goal of ERI is to enable specialists, computer scientists and algorithm experts with zero expertise in chip design to design system on chips. So DARPA is investing $100 million to build a true general-purpose silicon compiler. So what you see here is a very popular open board called Raspberry Pi, $25. It has sold millions of units to millions of developers over the last few years. We're talking professionals, hobbyists, students, and it's been a real enabler, right? So if you look at this type of a platform, you've got very complex SoCs that you see in the middle, with hundreds of millions of transistors, but you also have a fairly complex firmware and software development platform. So to do something like this today is out of scope for small teams. So if we look at the three components within IDEA, the silicon compiler. So we got design by intent. So if you look at this board, right, there's lots of components on it. And today, all design, every schematic, every circuit is bit exact, right? The designer really has to put down every detail, including which part number, which resistor, what kind of tolerances. So we need to raise that abstraction a lot so we can focus on actual features in the system rather than every single detail. So that's the first component. Second component is to stand up an open source ecosystem within hardware. So in software today, we take for granted that we can go up to GitHub, download components, libraries. We can mix and match, C++ code with Python code, and if you look around today in your smartphone, in a data center, there is open source everywhere. Very few of the largest U.S. companies today in software and services could have done that without open source. In hardware, we have nothing like that. So if we can stand up an ecosystem like that, then we have kind of ticked off the design and verification for a lot of known good components. And then finally, once you have the schematics, you need to lay out the polygons, some of the things that Lynn talked about, that creates the actual circuit, the board circuit, the package circuit, and the chip circuit. And that is excruciating. For a modern chip, that can take many, many months. So we're going to create an actual compiler. So when you think of a software compiler today, you go from source code all the way to executable. There's no little elf, there's no little people in the middle that have to go in and intervene. And that's the compiler part. So just digging in a little bit deeper, it's going to get kind of geeky here. For that thing on the left, there's a circuit. Don't worry if you don't understand what it is. So basically, the way things work today, right? You have very, very smart people. There are very few of them on this planet that do analog circuit design. And it's a very specialized science or art engineering, like a lot of black magic. So the engineer will create the schematic, the innovation, and then usually they'll hand it off to a drafting person sitting in the cubicle next to them, or maybe a whole department. And they'll go away and they'll create the polygons based on specification. So the specification is the schematic, but also a lot of sticky notes and verbal communication that describes how the circuit should be laid out based on prior knowledge. And then there's vocabularies, things like you should lay out the circuit in a centroid manner. You should isolate sensitive component from noisy component. And so you have a common language between the drafting person and the engineer. And so this is the way things have been done in analog design for a long, long time. And this is clearly not a compiler. This is a human compiler. This is manual labor. So the question is, can we actually take away that manual labor? If we have the schematic, and maybe the schematic we can even pass around and share it, can we actually automate that layout process? And it's been tried before with expert systems, very complex expert systems, but there were always gaps. So now we're taking a different approach. We're saying, well, we're going to take a data-centric approach. Instead of trying to fill in the rule for every case scenario, we are going to take known good designs, known good layouts from the past, and learn from them. Not exactly a new concept, but we're going to apply machine learning to circuit design. So what does ERI design look like at the end of the day? So to the programmer and the algorithm expert, computer scientist, I would hope that it looks and feels very much like software today, right? You can go and download repositories from GitHub, maybe create a patch, type make, and there you go. There are your blueprints ready to be manufactured. Just you have an executable today to run your program. For the manager, if we think about procurement and hardware design for real systems, it's the easy button. It's the build to order, right? Where you can actually think about an Amazon-style model where you have hundreds of known good designs. You don't have to build them up prior. You just press the button and you get a custom design out. For society, I think it could be truly disruptive, this idea of a silicon compiler. If you look at the last 50 years, everything in the semiconductor has been driven by economics. So it's, we sell more units at a lower price every year, and that's how we raise the revenue for the industry. But those high volume opportunities are far and few between. So there are many, many applications where it just doesn't make sense to design a chip because the NRE is too high. So, what are some of the applications that we can design if we reduce the NRE close to zero? I don't know. But I do know that a silicon compiler will be part of it, and I can imagine some amazing applications that could be enabled. Things like bots that can rescue autonomously, drones that can learn real time and actually fly and not have to be tethered to a data center, personalized diagnostics that are the size of a human cell. All these things require an intense amount of specialization, which is only possible with custom silicon. So that those are the kind of things that hopefully we'll enable with the ERI design program. Thank you.
All right, thank you very much. So we're going to dive into questions here. And, looking at my app here, which uploads the questions that are being voted on, it's very similar to my first question. Right? And you can just kind of tell where the head of the community is. It's all about security. Moore's Law was really about manufacturing, but then has been translated to performance, and that's the exponential that we've been on for years. The question from the audience actually is to Bob and Lynn. Through that arc of history, if you had it to do over again, would you have focused more on security and trust and not just ease of design and performance? So I get a hard one for you off the bat.
So let me take a crack at that. I mean, security shows up in lots of different ways. You can ask about whether a chip design was the way it was intended or has been affected, and how you deal with the kind of root of trust kind of issues. But security in a world where you're dealing with a big distributed system also engages the networks in a major way. I have been at many meetings where people have complained that DARPA never took security as a prime requirement up front, just never paid any attention to it. And let me just tell you for the record, nothing could be further from the truth. In fact, I was the manager of the very first security program for getting packet network security on the ARPANET, and the problem was not lack of interest. It was that the people we needed on our side so it could be used in defense were so overwhelmed with other challenges, they did not think networking was necessarily in their future. They wanted to wait until it was proven. And so the bottom line was we could not get the kind of support we needed. We got a little bit of support to use a crypto machine for a point-to-point equivalent circuit through the net. There was a lot of work on trying to understand how to build secure software systems, and a lot of that had different set of issues associated with it. But there was a lot of focus, too, in the early days of the VLSI program as to whether we should have a security component to that, and we never could get to the root of trust issue in the hardware sense, because if you could always mess with the hardware in some way, you could affect everything else that went on.
Great. Lynn, anything to add? You can pass to.
This actually reminds me of sort of this larger issue of how do we remain aware, let's say in a community of practitioners, whether it's medical doctors, police, military, whatever, how do we remain aware of emergent, just noticed security problems or issues where something has failed in our protocols, our methods, that perhaps could be exploited by adversaries? And in thinking about it, I really see that as a technosocial problem of the following kind. For example, in adventure sports, different kinds, you have different ethics about safety. And in one in particular, in running whitewater, for the years I was pretty active, there was a thing called the Whitewater Safety Report, okay? And it's just something that sprang up and became an integral part of the ethic of the community. Anytime, anywhere, there was a kind of unexpected sort of accident. Something had happened that was not, that sort of touched the edge of like, what we knew. It went around in this report to pretty much everybody that was active. And so whether you were a beginner coming up to the system or somebody far along, you began to sense the need to look out for that kind of thing. So I'm wondering how we get that into our design cycles.
Great. Well, hopefully quickly we can maybe touch the other members here, but you know, Andreas, you're making a bet on open source, and I know that you know, I think it's not obvious that open source leads to better security, but you know, potentially it does. So can you kind of walk us through your thoughts on that?
Well, I think one of the things you get when you do have the source code is you have an ability to mathematically prove that the circuit does exactly what you want it to do. And when you do get an opaque circuit, you just have to trust that the person designed the circuit did a good job. So that's, if you truly care about security, the ability to formally analyze and prove correctness is an important thing. So there's only a path towards that with having the source code.
Great. And Mark, your thoughts both on the security side and sort of the emergence of open source hardware from the industry perspective.
Well, on security, there's no question. It's an equal footing with performance and function, with what we do for power management and with security. I mean, you have to boot to a root of trust. You have to authorize every sub-element as trusted, and so that's has to be built in the architecture, and it certainly is in what we do in AMD. And you do learn going forward. You do find exploits you could have missed, and so what we are doing and everyone's doing is doubling down on that pre-silicon, pre-release of product, how you verify. In fact, we've increased 3x the number of verification cycles we throw at security. But going forward, I think what you're going to see is you know, even more and more novel architectures to protect information. It's fundamental. You can't have the growth in computing that we all expect if you can't trust that your data and your information is safeguarded. And with regard to open source in general, we're a big supporter. You look at some of the open source architectures that are out there. You see RISC-V starting to get adherence in CPU. You see what we've done. We've open sourced quite a bit of our software. So in general, a very vibrant open source community. It drives innovation and it drives better products, like Andreas was giving an example.
Great. One of the aspects that I thought was interesting through this course of history that we walked through was, Bob, you came from the computer science perspective and the networking perspective, and that was sort of evolving in parallel with sort of the circuit complexities that were emerging. And then you sort of merge those communities together with some of the MPW work and use of the internet for both dissemination of information and lowering the complexity. But when you come from a different field and apply it to another field, you're not always welcome, right? So when you make significant change, there's always friction. So you can talk a little bit about kind of how that played out in your.
Well, there were frictions, but not the kind I know the kind you're talking about can occur, but it really didn't because number one, the computer science world was in real trouble at the time, with lack of funding and being demoralized. So they were looking for something new to get into. And so they welcomed this kind of program. And industry as well was pretty supportive because they saw it producing, workforce for the future. The problem was not what you talked about, because the fact that I, in particular, had no real expertise at the semiconductor level, although I'm an electrical engineer by background, so I knew about transistors and circuit design and the like. I used to teach that at MIT, in fact. It was that I was not a competitor for any of the companies in the semiconductor business. I was not seen as a competitor. So they welcomed it. The bigger problem was that some of those companies wanted no part of it. Hewlett-Packard was one of the early participants, but we got many of those companies. IBM was one, Mostek was one. TI never got involved. I think they had state-of-the-art lines at the time, and they didn't want to expose the details. So that wasn't the problem. The bigger problem was the conflict between the physicists and the semiconductor experts who had been designing all these architectures in the past, and the fact that they may have all this competition from these kids in the schools who might have good ideas and could do it. And so there was this tension between a set of folks who were well known in the field and some of the pioneers who said, look, if you don't need something at the state of the art, use what is already out there. Use a microprocessor and just program it. Use a floating point gate array and just figure out the wiring to do that. And if you do need state-of-the-art, don't give it to a computer science person who wouldn't know. Give it to a physicist. And so for them, there was no middle. And without any middle, you can't train people. It sort of just hollowed out that whole area to the point where it wouldn't have existed. That was a big struggle. And fortunately, we succeeded. But there were powerful forces who were saying, hey, what do you think about that? Maybe we should just drop this.
So fast forward, 40 years or more, and Andreas, you're now looking at emerging principles like machine learning and open source and applying it down to the electronics level to try to manage a new level of abstraction. So what is your sense in terms of the willingness of the community to adopt?
So it's definitely a little hesitance on the status quo, the incumbents. I think that going through and realizing that open source is not a religion today, at least not for most. If we look at where the industry's gotten in software in the last 10 years, it's very much a mix and match mentality. People use permissive licenses, which means that you can mix your own secret sauce with open source. It's not viral. And so from an open source perspective, you just have to look at the economics. Does it make sense for you and the industry to share or not? But it's certainly raises some red flags with the status quo when you say open source. Like first reactions, whoa, no, we don't do that. But then when you talk about it, you realize it's not a big deal.
And why do you think, I mean, in the software domain, there's billion and now maybe $1 trillion company, right, that is really built on an open source software stack. So in the software community, right, there was broad adoption. In the hardware community, what do you think, I'll go to Mark, what do you think is a representation of industry, right, that has built sort of the dichotomy of how we view these different problems?
Well, I think part of the challenge that the industry's seen from a hardware standpoint is actually what I discussed earlier. It's actually really difficult to stay on that historic pace of Moore's Law and performance improvement while staying in those constraints that we all face, that you all as consumers expect. And so it's driven an innovation that is very hard to do at that same rate and pace when engineers don't have the freedom to innovate. And so if you put too many constraints on such that it's completely shareable and open source, you're going to have some trade-off. So as soon as you abstract up a level, you're going to have some trade-offs. My view is that there's a need for both. You're still going to need that kind of cutting-edge innovation. And so at the lowest levels of a hierarchy, you're still going to have tailored implementations that are giving every ounce of performance. But as you start raising up an extraction level, I think there's tremendous room for open standards on how those get connected together and to build these heterogeneous systems to keep us on at or exceeding the paces of historic performance that we've had. And even at the lowest levels of hierarchy, look at field programmable gate arrays today. They're already out there to allow you to, very quickly take an innovative design you may have and instantiate it in silicon.
So, here we are. Some people are celebrating the end of Moore's Law. I don't actually, I wouldn't celebrate, but it actually is not true, right? Scaling is still ongoing, but we're at an inflection. It's this cost economic-driven inflection that's going to change how we view scaling, even if it occurs. So some people have sort of a defeatist attitude in the electrical engineering community that this is the end of a road, right? But some people are wildly optimistic, like myself. So Lynn, you kind of were part of this in the past where there were some predictions on the end of performance, and you stepped in and made change. So any recommendation to us?
One of the things as I've been listening to the presentations that's kind of strikes me is that Moore's Law and thinking about it as a way of measuring progress is kind of like, it's sort of roughly analogous to using GDP as a way of measuring our progress as a nation. And sort of one, in effect, linear measure seems weak. It doesn't cover. It does in times of sort of ongoing progress in the absence of external perturbations. But in times of rapid change, it doesn't. So one of the things that I don't have any answers to, but wonder about is what would be some better measures of our progress that included measures of the human engagement, the human involvement, measures of human empowerment. How do we measure how far we are along in the directions we're going? And what you can measure, you can kind of animate, guide, channel, and so forth. So I just leave that as a kind of open question. I would leave with a question.
All right. Well, I could do this all day. This is some of my heroes that I grew up admiring and learning from and admire in terms of how they've been able to capture the industry that they're leading right now. Fortunately, I got a red blinking light here that's telling me we're over time. So why don't we thank our guests?